Hello everyone and welcome back to another Stat231 tutorial. We're quickly making it towards the end of term and I hope that is going well for all of you. A small bit of housekeeping before we get started today. This tutorial is for week 10, which leaves us with 2 more after today. In week 11, we cover hypothesis testing for multinomial data and running goodness fit tests. In week 12, we consider two-way contingency tables and briefly look at how we can establish causal relationships with statistics. With only 2 videos left, I want to put it out to the class. If there are any concepts from the term that you would like to see me dig into in more detail, or that you would like an explainer on, or an example problems of, or a deeper dive into, please email me and let me know. If there are any concepts you are still struggling with, anything that's not clear that has come up, I'm happy to cover those in the last couple of weeks, getting you ready for the exam. If I do not hear from you, I will continue to make these videos as I have been, but if you would like to have a say in what we talk about, please let me know. With that, on to this week's video. Over the past week, we began to look at 2-sample hypothesis testing. Related to this and to questions that I have been receiving regarding Quiz 7, I wanted to try to put a context around hypothesis testing in general. I want to take some time today to summarize all of the concepts that have been covered and fit them together into a cohesive picture for you all. I will then show numerous examples of the types of hypotheses that we could test, and we can use the presented framework to decide on what would be appropriate. That will likely take up the entirety of the tutorial time today, but I'd encourage you to think about why these types of sample tests are included after the linear regression models. If you would like to know more, send me an email and I can explain. To begin, I will recap the basic 4-step process for testing a hypothesis. First, we decide on a null hypothesis. Then we work out a discrepancy statistic that measures the level of conflict that our observations have with the null hypothesis. Third, we compute a p-value, which gives the probability of observing a discrepancy measure at least as extreme as the one that we observed, assuming that the null hypothesis were true. Finally, we take the p-value and make conclusions. Now, calling this a 4-step process hides some of the complexity within it. At each step, we have decisions to make. Depending on the decision that we do make, we will end up running different tests. So let's begin to talk about what those decisions are and work out how we can fit everything we have learned together. Note, everything that I'm presenting is based around the material in Stat231. There is additional complexity that can be layered on top of this. If you continue into statistics, this will serve as a starting point to build from. Further, this is a framework that's implicitly assuming that we're testing model parameters. Tests regarding distributions will be similar, but they add additional considerations onto this. Let's start with decisions related to the null hypothesis. Now, some statisticians, and this is included in your course notes, always suggest using the same null hypothesis, namely theta equal to some value. There are some good underlying reasons for this, but in this framework the implicit decision you are making is then, what is the alternative hypothesis? I prefer personally to treat the null hypothesis as possibly directional. That is, we can have theta equal to a constant, theta less than or equal to a constant, or theta greater than or equal to a constant. In this framework, we need not consider the alternative directly because it is implied by our null. That is, if our null is theta equals a constant, our alternative will be theta not equal to the constant, and so on. An important point here, if you do choose to use my framing, the null hypothesis always needs the equal sign. You cannot have a null hypothesis of theta less than a constant. It needs to be less than or equal to. The reason is, in part, that when we have to compute the p-value, we need a value of theta to work with, and that has to be a value under the null. Functionally, there's no difference between choosing a null that is possibly directional or specifying an alternative. The test statistic, p-value, and conclusion will be exactly the same. The question is just whether it's easier to think of an alternative or a directional null. You're free to do either. With that, the first consideration is whether we have 1 or 2 samples. Chapter 5 and the early parts of Chapter 6 dealt with hypotheses related to a single sample, while Section 6.3 dealt with 2-sample tests. This decision is one of the more objective choices to make. If you're comparing 2 samples, you want a 2-sample test. If you have only 1 sample, you want to run a 1-sample test. The tests are not as distinct as they may first appear, but for analyzing our framework, we first decide whether there are 1 or 2 quantities that you are testing. If there's 1 sample, then we wish to test regarding theta. In this case, our null hypothesis is going to take the form theta compared to some constant c. The next choice is to decide what direction we are using for the comparison. In particular, we have to decide whether we are looking at a 1-tailed or 2-tailed hypothesis test. How can we decide this? The basic idea is to consider what type of evidence are we concerned with. If we're only concerned with evidence in some direction, does a drug heal more often than random chance? Does a coin turn up heads less than half the time? Is there a positive impact of advertising on customer behavior? Then we wish to use a one-tailed hypothesis test. If, on the other hand, we are simply looking for evidence of a difference, does a drug perform differently than some baseline standard? Does a coin appear biased? Is there any effect of advertising on customer behavior? Then we're concerned with a two-tailed hypothesis test. We'll look at plenty of examples after finishing this framework, but the general question I would ask myself when determining whether we have a one-tailed or two-tailed test is, what constitutes evidence against my null hypothesis? If the answer is only observations that are above or below some threshold, then we have a one-tailed test. If the answer is anything that is far from expected, then we have a two-tailed test. If the test is two-tailed, then our null hypothesis is easy to determine. We will always take it as theta equals the constant of interest. This has an implied alternative hypothesis of theta is not equal to the constant. If the test is one-tailed, we have one further decision to make. Is it an upper-tailed hypothesis test or a lower-tailed hypothesis test? To decide this, we return to the question we just asked. What constitutes evidence against my null hypothesis? If only high values constitute evidence against the null, we call this an upper-tailed test, and we define the null hypothesis to be theta less than or equal to the constant. If, on the other hand, we consider values less than our cutoff as evidence against the null, this constitutes a lower-tailed test, and we define the null hypothesis to be theta greater than or equal to the constant. For an upper-tailed test, we have an implied alternative of theta greater than the constant, and for the lower-tailed test, we have an implied alternative of theta less than the constant. That covers getting to the statement of the null hypothesis for a one-sample test, but what happens with two samples? If there are two samples, then we wish to test regarding theta 1 and theta 2. We have a similar choice to make regarding a two-sample test as we did with the one sample. Do we care about any difference or a particular difference? This boils down to a question of one-tailed or two-tailed tests again. If we wish to know only if there is a difference between the two quantities, say whether two drugs perform differently, whether two coins show up at heads at different rates, or whether the two ads impacted customer behavior in a different way, then we are concerned with a two-tailed test. If we wish to make a directional claim, whether drug A performs better than drug B, whether a toonie comes up heads less than a loony, or whether a YouTube ad generates more revenue than a TikTok ad, we are interested in a one-tailed test. If we wish to perform a two-tailed test, once again our null hypothesis is easy. We simply take the null to be theta 1 equals theta 2, with an implied alternative that theta 1 is not equal to theta 2. If we wish to use a one-tailed test, we have to make a further decision. This decision is similar to deciding upper or lower tailed in the one sample case, though in some sense it's slightly easier. Here we have to decide which is higher under the null. This will normally be clear based on the question that we are asking. If we wish to test whether the effect of a new drug, theta 1, is better than the effect of an old drug, theta 2, then our null hypothesis is going to be that theta 1 is less than or equal to theta 2. This way, evidence against the null is what we care about. Making the decision of which is higher will lead to a null of either theta 1 is less than or equal to theta 2, or theta 1 is greater than or equal to theta 2. The implied alternatives are then theta 1 greater than theta 2 or theta 1 less than theta 2, respectively. With those decisions, we have come to a null hypothesis. This null is going to inform the remainder of the test, and it's imperative that you select the correct null in order for your test to be performed correctly. Before moving on to stage 2, I will give some additional advice here. First, it is always worth asking what counts as evidence against the null. This helps to inform what your null hypothesis should be, whether it's directional, and so on. Second, it's important to remember that we never get evidence in favor of the null hypothesis. We can only get evidence against the null hypothesis. As a result, if you are hoping that you observe a particular relationship in the data, that one drug is better than another, or that one ad is particularly effective, you must take the null hypothesis to be the complement of that. Let's take the example of an advertisement. Let's say you wish to know whether a particular ad you are showing leads to a desired action for more than 5% of people who see the ad. In this case, you must set the null hypothesis to be theta is less than or equal to 5%. Why? Well, let's say that you observe an impact on 12% of people in the data. If you had taken the null hypothesis to be theta greater than or equal to 5%, then the best that you could hope to conclude is that there is no evidence against the null hypothesis. If instead you take the null to be theta less than or equal to 5%, then you could possibly conclude that there is strong evidence against the null hypothesis, which is suggestive of the statement that you care about. Third, in a two-sample test where you care about the direction, it's not strictly necessary that you consider the two possible hypotheses as separate. The reason is that theta 1 and theta 2 are typically just labels we put on the parameters of interest, and we can always label the problem in such a way to make the null theta 1 less than or equal to theta 2. If we are faced with a problem where the null would be the opposite, that is, theta 1 larger than or equal to theta 2, we could just simply call theta 2 theta 1 and call theta 1 theta 2, and then continue with the aforementioned null. Once you have decided on your null hypothesis, you get to move on to deciding on your discrepancy measure. The good news is that the discrepancy measures are largely informed based on the null hypothesis that you've just written down. Before we can write down the discrepancy measure, we need to make a decision which may seem like it should wait until the p-value part of the hypothesis test. What method are we going to use? For the purposes of this course, when testing distributional parameters, this question likely has one of three answers. We are either going to use an exact method, an approximate method based on the central limit theorem, or an approximate method based on the likelihood ratio. The reason that we need to decide this is because the statistic that we use will be dictated by the type of test we are going to perform. Fortunately, the type of test that you will be using in this course will almost certainly be given to you. If there is a hypothesis test which could be performed in more than one way, this would have to be clarified to know which we are expecting. As some general guidance, if possible, exact tests are preferable to approximate tests, especially when the sample sizes are small. Now, it's worth taking a moment here to clarify exactly what we mean when we say exact. An exact test, or an exact p-value, is one where the distribution that we use to compute the p-value is exactly correct, given the null hypothesis. This tends to involve working with probability distributions directly, though we do have some pre-specified results that are exact. Think about the Gaussian test for means. If we know the standard deviation, then we can use results from the Gaussian distribution to run an exact test, computing p-values with a g01 distribution. If we need to estimate the standard deviation, then we can run an exact test with a t-distribution. We've also seen exact tests based on the binomial distribution. If you are told to use an exact test, you need to think critically through the distribution that we should use. If, on the other hand, you are told to use an approximate test, either based on the CLT or LRT, then we have a more predefined statistic to work with. First, let's assume that we wish to compute the discrepancy using an exact test. In this case, there will generally be multiple different ways of computing a test statistic, but we can give some guidance for this course. Remember that D is meant to measure how unusual a particular outcome is, based on what we would expect to observe if the null hypothesis were true. In this course, we also tend to take D equals 0 to mean no disagreement with the null, and D greater than 0 to suggest increasing deviation from null expectations. Let's begin by considering our one-sample tests. As a basic starting point, we can take D to be the absolute difference between the maximum likelihood estimate of the parameter of interest and the expectation of that parameter if the null hypothesis were true. That is, we can write D equal to the absolute difference between theta tilde and theta naught, where theta naught is the value under the null. If you have a two-tailed one-sample test that you wish to be exact, this usually will suffice as your D. You may wish to scale it for distributional results, but we'll comment on that for the next step. Why does this work for a two-tailed test? Well, notice that if the estimated value is far from what we would expect in either direction, we'll have a large value of D. If, on the other hand, the estimated value is close to what we would expect, whether it's larger or smaller, we would have a small positive value. If it's exactly what we would expect, the value is 0. This conforms precisely to what we wish D would measure. If instead of a two-tailed null, you are considering a single tail, this discrepancy measure no longer works. Why? Well, as discussed, it treats evidence above and below expectation as equivalent. This is not what we want for a one-tailed test. However, this still gives us a good starting point for the discrepancy measure. Let's say you're considering an upper-tailed test so that the null hypothesis is theta less than or equal to a constant. In this case, we only want high values of our estimated theta as evidence against the null. If we simply drop the absolute values from our previously considered D, we take the discrepancy measure to be theta tilde minus theta naught, and this is a good start. Notice that when our estimated value for theta gets large, then d will get large. However, what happens if our estimated value is small, say below theta naught? If we observe this, then we should expect that our test concludes that there is no evidence against the null hypothesis. However, based on d equal to theta tilde minus theta naught, we would actually have d being a negative number. This may not be a problem, and there are times beyond this course where you will see this being used. In Stat 231, we wish to cut off discrepancy measures at 0. As a result, we suggest modifying this to be the maximum between theta tilde minus theta naught and 0. This has all of the properties that we want from a discrepancy measure, and it seems to suffice. What if, on the other hand, we wish to test a lower-tailed test? How can we naturally extend our discrepancy measure to this case? Well, here we want values of theta tilde which are less than expected to create large values for d. What if we take d to be the maximum between theta naught minus theta tilde and 0? This will work exactly opposite to the upper-tailed discrepancy measure. What about two-sample tests? Well, there is one method for thinking about two-sample tests that I find to be useful for consolidating this framework. If you think about the relation stated in the null hypothesis between theta 1 and theta 2, then we can rewrite this as a relation between the difference between theta 1 and theta 2 and 0. If our null hypothesis is, for instance, theta 1 equals theta 2, then this can be written equivalently as theta 1 minus theta 2 equals 0. If we then think about theta 1 minus theta 2 as a parameter itself, this looks like a one-sample test of the hypothesis theta equals 0, which we have seen uses the discrepancy statistic of the absolute difference between theta tilde and the constant we are testing, which in this case is 0. One reason that I like thinking about hypotheses in this context is because it gives us an easy ability to expand the types of two-sample hypotheses we can test. For instance, what if you believe that theta 1 is the same as 2 times theta 2 plus 3? Well, this would be encoded as a null hypothesis of theta 1 equals 2 times theta 2 plus 3. Now, if we rearrange this quantity to look like a one-sample test, we get the equivalent null hypothesis of theta 1 minus 2 times theta 2 equals 3. By treating our statistic of interest as theta 1 minus 2 times theta 2, we can immediately read off the discrepancy value as the absolute difference between theta tilde and 3, where theta tilde is given by theta 1 tilde minus 2 times theta 2 tilde. We can use this exact same strategy for one-tailed two-sample tests. If we rewrite them as theta 1 minus theta 2, and then derive the upper-tailed discrepancy measure as the max of theta 1 minus theta 2 and 0, and the lower-tailed measure as the max of theta 2 minus theta 1 and 0. Of course, as previously noted, the two-sample datasets oftentimes can be interchanged as needed. That is, we only need to consider theta 1 less than or equal to theta 2, because if we wish to test the other hypothesis, we could change which is which. Now, it's worth noting that these discrepancy measures will not always work in exact tests, and this is part of why an exact test can be challenging. The test statistics for tests of variance, for instance, do not follow this form. We also find that for Gaussian exact tests, we need to scale the discrepancy d here by the standard error to derive either the exact Gaussian or exact t-distribution that we desire. These are the types of results that you will need to know in order to apply in any given scenario, and it's also worth looking through the relevant tables in the course notes which summarize the common tests alongside their test statistics and p-values. In particular, we can consider which of those are marked as exact versus approximate. Now, part of the motivation for the exact discrepancy statistics that we have considered is that these form the basis of the CLT-based discrepancy statistics that we're interested in. In particular, remember that an estimator of a sample mean, if your sample size is large enough, will approximately follow a Gaussian distribution with a mean given by the mean of the estimator and a standard deviation given by the standard deviation of the estimator. In particular, what this means is that whenever theta is represented by a sample mean, we can turn these discrepancy measures into relevant test statistics by simply dividing by the relevant standard deviations. The exact scaling factor is going to depend on the underlying situation. The form of this is provided throughout the different sections of the notes. You should feel comfortable deriving the standard deviation for the common distributions, and you should keep on hand references to the different standard deviations which are applied for two-sample data. Still, when applying the CLT, we can take our previously defined discrepancy measure, divide it by the standard deviation of theta tilde, or equivalently use an estimate of it, and then use the normal approximation. The final method we consider in this course is the likelihood ratio statistic. This test statistic does not use the same discrepancy measure, and in fact, in any event, the test statistic for a likelihood ratio test will be the same. Here we take d equal to -2 times the log of the relative likelihood, evaluated at the null value. Now we generally only apply the likelihood ratio test to a two-sided test. The reason is somewhat subtle, but it has to do with constructing the appropriate likelihood function. We can think of the likelihood ratio as constructing a ratio between the likelihood value that we care about in the numerator, which for our situation will be theta naught, or the null value, and the likelihood that will be most likely under the alternative. We tend to think of this as simply the maximum likelihood value, but in fact it should be the maximum likelihood under the alternative. What does all of this mean? Well, in general it means that in a one-sided test we will use alternative procedures within the confines of this course. So far, let's recap. We have considered determining our null hypothesis and used the null hypothesis and desired test to determine our deviance statistic. What comes next? Well, luckily for you, the rest is up to routine calculation. The idea is to take our test statistic d and, using distributional results, either exact or approximate, compute the probability that d is at least equal to our observed value if the null hypothesis is true. For exact p-values, that means assuming the null hypothesis is true and computing the probability directly. For our approximate methods, it means applying the results of the CLT or LRT and using either a Gaussian or chi-square distribution for the p-value. There are plenty of examples throughout the book and in the practice problems to compute p-values. I would recommend working through some of these until the process feels like second nature. Finally, we take our p-value and interpret it. Remember, our p-value only serves to provide varying degrees of evidence against the null hypothesis. The smaller the p-value, the stronger the evidence against the null. If you are not entirely sure how to interpret p-values, I'd recommend watching back 2 tutorials where we discussed exactly this. To finish up this discussion before diving into some examples, I want to recap the types of two-sample tests that we looked at. There are 3 questions to ask ourselves when we're looking at two-sample data. First, are the data paired or unpaired? Paired data refer to observations in 2 samples that correspond to each other. Say, for instance, we're interested in the durability of 2 competing car tire brands. If we try each brand of tires on a set of, say, 50 cars, where each car gets each set of tires once, then we can think of these data as being paired. We observe the same car twice, once with each set of tires. If, on the other hand, we try the first tire brand on 50 random cars and the other tires on a different set of 50 random cars, then these data are unpaired. There's no natural grouping between the 2 sets of data. Paired data are not treated as two-sample data. Instead, we consider these data to form a single sample where the observations are given by the differences between the first and second sample. Then, this difference series becomes a single sample of data for us to consider. If instead the data are unpaired, we continue thinking of them as coming from 2 separate samples. Second, are the variances known or unknown? If we know the variances, we will typically use them directly and can compute exact test statistics based on the sample. But this is not common in practice, though when it does happen, it simplifies the situation greatly. If the variances are unknown, we will typically have to estimate them and then use our estimated values in place. If the variances are unknown, then we have to ask the final question, are the variances equal or unequal? While it may not be the case that we know specifically the value of the variance takes on, we may nevertheless feel comfortable assuming that the 2 samples have the same variance. If so, we can pool the information from the 2 samples to compute a pooled variance estimate. Otherwise, we need to work from the estimates of the 2 individual variances. The pooled variance estimator is provided on page 247 and involves taking a weighted average of the 2 individual variance estimates. If one of our 2 samples is larger than the other, it gets more weight. If the variances are unequal and we use separate estimators, they will usually be combined through a simple addition procedure. All of this is summarized in tables 6.3 and 6.4 in the course notes. There's a lot here. What I want to do next then is to provide a good chance to practice working through some of these details. To begin, I will read off some scenarios, and you should try to determine what the null hypothesis is. I would encourage you to read through the scenario, they should be typed out somewhere on this video, and try to discern for yourself what the null hypothesis will be. After I've presented the scenario, I will explain the answer. Scenario 1. You wish to know whether the average time to graduation for math majors is less than the average time to graduation for physics majors. In this first example, we are dealing with two samples. We have information for math majors as our first sample and information for physics majors as our second. Now, if we take theta 1 to be the average time to graduation for math majors and theta 2 to be the average time to graduation for physics majors, then we want to know whether the average time for math majors, theta 1, is less than the average time for physics majors, theta 2. Since we are concerned with a particular direction, we know that this is a one-tailed test, and in particular, we will take our null hypothesis to be theta 1 greater than or equal to theta 2, so that we can determine how strong evidence against this claim is. Since this would be a two-sample test, we need to decide whether we are willing to assume that the variances are equal between the two populations or not. This is something that would be informed both by our data and by the underlying subject matter. If we assume that the variance in time to graduation is equal between math and physics majors, we would use a pooled variance estimator. Otherwise, we would use the individual sample variance estimators. Scenario 2. The NCAA claims that the average graduation rate for student athletes is 85%, but you're skeptical. These data are one-sampled. We only have one source, that being the graduation rates of student athletes. Moreover, there is no indication that we have a suspicion of one direction here. We do not seem to have a reason to care if the true graduation rate is above or below, and as a result, this is a two-tailed test. Then our null hypothesis becomes theta equals 85%. Here, we are letting theta equal the graduation rate of student athletes. Scenario 3. This year has been difficult due to COVID, but you wonder whether there was something else going on. You theorize that maybe the temperature this January was different than average, about negative 6.5 degrees Celsius. Once more, here we are only concerned with one sample of data, the weather in January. Furthermore, we do not seem to care about a particular direction of difference. We are not asking whether it was colder this year or hypothesizing that it was warmer. We are just hypothesizing that it may have been different than average. Then, taking theta to be the average temperature in January, we take our null to be theta equals negative 6.5. Scenario 4. There are plenty of reports regarding the efficacy of COVID-19 vaccines. Is the reported efficacy of the Pfizer vaccine different than the reported efficacy of the Moderna vaccine? This example pulls on two sources of data, and so it's two-sampled. The question is whether or not there is any difference, not whether there is a particular difference, and so our test is two-tailed. If we define theta 1 to be the efficacy of the Pfizer vaccine and theta 2 to be the efficacy of the Moderna vaccine, then this simplifies to a null hypothesis that theta 1 equals theta 2. Here again, we would need to make a decision regarding pooled variance. To reiterate the point, if we suspect the variance in efficacy related to Pfizer and the efficacy related to Moderna were sufficiently similar, then we could use a pooled variance estimator. Scenario 5. Continuing on regarding vaccine efficacy, the J&J vaccine has been reported as less effective than Pfizer. Is the Pfizer vaccine really better? Continuing from above, we still have two sources of data. This time, the trial results from Pfizer and those from Johnson & Johnson. However, here there is a more specific claim, that Pfizer is more effective than J&J. As a result, we have a one-tailed hypothesis test. Since we are making a directional claim, we make the null hypothesis of the opposite and see if there's evidence to reject it. By keeping theta 1 as the efficacy of the Pfizer vaccine and taking theta 2 to be the efficacy of the J&J vaccine, we can write our null hypothesis then as theta 1 is less than or equal to theta 2. Scenario 6. It is frequently discussed that Stat 231 can be quite a challenging course. We want to know whether its level of difficulty is different than the difficulty of Stat 230 by checking how students who have taken both performed in either. In this case, it appears as though we have two samples, student grades in Stat 230 and student grades in Stat 231. Note that we are taking the same set of students for both, however, which makes these data a natural candidate for paired testing. Since these are a two-sampled paired dataset, we can equivalently think of them as a one-sampled dataset. Now, letting theta 1 be the grades in Stat 230 and theta 2 be the grades in Stat 231, then we can define theta to be the difference in these grades, that is, theta 1 minus theta 2. In words, theta then represents how much higher a student's Stat 230 grade was compared to their Stat 231 grade. Noting that our question is simply, are these courses similarly difficult, we are not particularly concerned with a direction, and we can write the null hypothesis either as theta 1 equals theta 2, or equivalently as theta equals 0. Note that while this is a two-sample test, because it is paired, we are actually considering the one sample created by differencing the observations. As a result, we are not concerned with deciding between the pooled and standard variance estimators. Scenario 7. You see advertisements from an individual who claims to be a Stat 231 tutor who can, quote, help students earn on average higher than 90% on their quizzes without studying. This claim could be tested using just one source of data: the marks of the students that have used this tutoring service. Moreover, there is a very specific directional claim, and in particular, it's an upper tail test. As a result, we take theta to represent the average grade of the students who have used the tutoring service, and the null hypothesis is theta less than or equal to 90%. Scenario 8. The same Stat 231 tutor is looking at the efficacy of their advertisements, but suspects that students may be too clever to fall for the obvious scam. They wonder if their ads are being acted on by fewer than 2% of people who see it. Just as the student results required only one sample to test, so too do the advertising results. In this case, we would take theta to represent the proportion of students who saw the ad and acted on it. Then, since the individual wants to know whether fewer than 2% of people are acting on the ad, we would take the null hypothesis to be theta greater than or equal to 2%. Scenario 9. You wonder whether twins differ in average height based on whether they are the older or younger twin. In order to investigate this question, we would need data on pairs of twins. As this seems to suggest, this constitutes two-sample paired data, where we conceptualize the height of the older twin as theta 1 and the height of the younger twin as theta 2. Then we are concerned with theta 1 minus theta 2. Equivalently, we could count each set of twins as a single unit and use the difference in their heights, older minus younger, as theta. This is, of course, exactly the same thing. The question at hand did not wonder whether older twins were taller or shorter, but rather whether they had a different height on average. This suggests using a two-tailed test, and in particular, taking the null hypothesis to be theta equals 0. Scenario 10. A medical research firm claims to have invented a device which accurately reads a patient's blood pressure. Regulators want to test the device to see if its accuracy is any different from a standard blood pressure cuff, so they recruit volunteers to have measurements taken by both. This final example is one where the procedure matters intensely. If, as suggested by the question, we use each device on each patient, then these data are paired. Just as with our other paired samples, we could define theta to be the difference between the new device and the standard blood pressure cuff. Then, since the regulators are interested in whether or not the measurements are equal, we would take the null hypothesis to be theta equals 0. I hope that these examples were helpful to determine what type of test we are running. Once you have determined the type of hypothesis to test, the work becomes more routine. There are numerous examples throughout the course notes and in particular at the end of chapter problems to reinforce these ideas. These questions tend to give you the null hypothesis and ask you to test the problem. I would advise working through this. The types of calculations are fairly routine mathematically, but there are hurdles to watch out for. Still, when you can identify the scenario you're working with, you are well on your way to solving the problems. As a reminder, if there are any topics you would like me to cover in the remaining 2 tutorials, please reach out and let me know. I'm happy to go back over anything from the course that remains unclear. If not, I hope that you found today's tutorial helpful, and as always, if you have any questions, please send me an email to ask. Thank you all for watching.